Alright, my friends, this is it. This is the very last Calculus 2 video I got for you. After this, nothing but a final exam and then a blissfully calculus-free existence for you. Maybe. I might see you in Calc 3. So, if this is to be the end, let it be a worthy end. I have here a polar function. It's one of my very favorite polar functions. This is the function that you can use to make a heart shape, because of how much I love you and calculus. Function literally looks like this. It's called a cardioid. It's good. It's good times. And for this video, this last video, I'm going to find the derivative of this function, and then I'm going to solve pieces of that derivative. I'm going to set pieces of that derivative equal to 0, so I can solve for all of the points on this shape where the derivative is 0, and all of the points on this shape where the derivative is undefined, and maybe a special weird third case that we'll talk about when we get there. So, strap yourselves in. There's going to be a lot of heavy-duty math going on. It's going to be a real good time. First, I need x's and y's. X is r cosine theta, so that's 2 minus 2 sine times the cosine, which I can simplify into 2 cosine theta minus 2 sine theta cosine theta. That's my x value. Y equals r times the sine of theta. So this is 2 sine theta minus 2 sine squared theta. Once again, we're going to take some derivatives of this, and we have our sine times cosine business here, and we have our sine squared here. So, as promised, one of these is a product rule, the other one is a chain rule. That's going to happen all the time. Let's just fly through it. dy equals 2 cosine theta minus 2 times the quantity. Derivative of sine squared should be 2 sine theta times cosine theta, which is, can clean this up a little bit, 2 cosine theta minus 4 sine theta cosine theta. dx is going to be the derivative of this. Oh, forgive me. This is not becoming quality I wanted delivered to you on my last video. We need some d's. Okay, now that we haven't forgotten those, we can move on to our dx. dx is the derivative of 2 cosine theta, which is going to be negative 2 sine theta. That other negative 2 is just a coefficient that's safe. And we remember from the last video that the derivative of sine cosine is cosine squared theta minus sine squared theta d theta. And I can once again clean this up a little bit. I got a minus 2 sine theta. I'm going to say that this is plus 2 sine squared. Actually, no. I want the sine squared in front. I'm going to sort of standard form this guy. I'll put the positive 2 sine squared as the first piece. I'll put a negative 2 cosine squared as the second piece, and I'll put this minus 2 sine as the last piece. D theta, we all know, applies to the whole thing. So, when I do my dy dx, I should get 2 cosine theta minus 4 sine theta cosine theta all over 2 sine squared theta minus 2 cosine squared theta minus 2 sine theta. And the d thetas on the top and the bottom will cancel out, and this is it. She's a beauty, ain't she? So many sines and cosines. It's incredible. I need to erase pretty much all of this because I haven't even started setting things equal to 0 yet, and I'm out of space. So if you need to see this more, pause the video, rewind the video, rewatch the video. You have all of these options. Okay, I have my derivative here, and once again, I want to find all the points on my lovely heart shape where the slope is equal to 0. These will be the maximums and the minimums on my heart shape. So probably there'll be one over here, probably there's one on the bottom. I can already guess what this one is. I bet there's going to be one at 3 pi over 2. 3 pi over 2 is the angle that's going to point me straight down. Seems like I should have a min there. We can find out for sure by doing this math. There might be one in the middle. There might be some weird nonsense in the middle. We need to talk about the middle more, but not right now. I'm going to set the slope equal to 0. Again, that means set the top equal to 0. And so we get 2 cosine theta minus 4 sine theta cosine theta equals 0. And, as we always do when we have something that looks ugly and equals 0, we're going to factor it. Both of these things have a cosine, and I can probably pull out a 2 as well. So 2 cosine theta times 1 minus 2 sine theta equals 0. So now I have the product of two different things is equal to 0. And I just need to figure out what makes this 0. Things that make cosine 0 are pi over 2 and 3 pi over 2. I also need to find out what makes 1 minus 2 sine theta equal to 0. I'm going to slide up here for that. 1 minus 2 sine theta equals 0. That means that 1 equals 2 sine theta, and that 1/2 equals the sine of theta. And that means that theta, on one lap of the unit circle, theta should be pi over 6 or 5 pi over 6. So let's pause and consider where these points are. Looking at this, we already sort of guessed that we ought to have one slope of 0 thing over here. We'll probably have one over here. We'll definitely have one at the very bottom. As predicted, 3 pi over 2 is one of our answers. At the angle 3 pi over 2, when you're aimed straight down, you get this point right here. You got a slope of 0. This is a local minimum. This point, I always kind of psych myself out about this point and this point. Every time I do this problem after not having done it for a little while, I trick myself into thinking that this should be a pi over 4 angle and a 3 pi over 4 angle. Like, I expect these to be in the middle, but they are not in the middle. They are sort of lopsided. These are on a 30-degree angles. This is our pi over 6 angle. This is our 5 pi over 6 angle. Here's our 3 pi over 2 angle. This thing in the middle, this pi over 2, That's this point right here. And we need to talk about that a little bit more before I'm ready to commit to that being a local max or min. So I'm going to erase some of this work. I'll leave some of it around. I'll leave the answers here, and then I'll erase where the answers came from. Okay. We want the slope to equal 0 on our beautiful cardioid. We have discovered that that happens when theta equals 3 pi over 2. That's the bottom. It's the one we guessed from the start. Pi over 6 and 5 pi over 6 are the two lumps of our heart. And then pi over 2 is some question marks. We're going to talk about pi over 2 more. First, I want the slope to be undefined. And if the slope is undefined, that means I want to set the bottom equal to 0. This is the bottom. I'm going to set it to 0. It's going to get weird. Here we go. 2 sine squared theta minus 2 cosine squared theta minus 2 sine of theta equals 0. This thing right now is kind of a gross looking mess. I've got sine squareds, I've got cosine squareds, I've got sines. Like there's 3 different things here, and there's not a lot I can do to unite them. But I do see that 2 of them are sine. I have a sine squared and I have a sine. If I could transform this into some sort of sines, then they would all be in terms of sine, and I could swap out sine for any old placeholder variable like a q or a v or anything. D. No, D is for derivative. A. A is very neutral. I'll call it A. If I can turn this into a sine, I can set sine equal to A, and then this thing would just be some straightforward quadratic. I could solve the quadratic. I could swap out my A back for a sine, and then go from there. And I'm going to do that by transforming this cosine squared into 1 minus sine squared using the Pythagorean identity. And then I'm going to simplify this out a little bit. I have 2, oh, that's squared. 2 sine squared theta minus 2 plus 2 sine squared theta minus 2 sine theta equals 0. It's really easy to lose track of some symbols in this. This is kind of a mess. I don't think I need this derivative anymore. You have served your purpose, derivative. It's time for you to go. So, I'm going to swap out my sines for just some random placeholder. I'm going to use A. A seems reasonable. And then I'm going to rewrite this a little bit simplified. I have 4 sine squareds, so I'll call that 4a squared. I have negative 2 sine here, so that's negative 2a minus 2 equals 0. Oh, not 2a, sorry. This is just a minus 2, and that all equals 0. And this is now just a quadratic. So I can divide by 2. 2a squared minus a minus 1 equals 0. I can factor this out pretty easily, honestly. I need a 2a and a 1 and an a and a 1. This will give me the 2a squared on the front end. the 1 on the back end, I need to use a positive 1 and a negative 1 in here if I'm going to multiply them to get negative 1. And I think this one has to be negative so that the middle terms give me a negative 2 and a positive 1 to add to the negative 1. Yeah. So 2a plus 1 times a minus 1. This should give me 0. So a equals negative 1/2 here, or 1 from here. So now, I hope you weren't counting on seeing this whole process start to finish, because I definitely do not have room for that. We're going to come back up here. A equals negative 1/2 or 1, and remember that A was the sine of theta. So sine theta equals negative 1/2 or 1, which means that theta, I'm going to use a different color for this so I can draw on my pretty heart. Let's go with blue. If the sine of theta is negative 1/2, that means theta needs to be 7 pi over 6 or 11 pi over 6. And if the sine of theta is 1, that means theta was pi over 2. So 7 pi over 6 is down here somewhere. You can tell I drew this a little bit wrong. My heart should be much fatter, should be much more full of love for calculus. But 7 pi over 6 is here. This is the point that ought to have a vertical slope. 11 pi over 6 is here. This is the point that ought to have a vertical slope. And pi over 2 is, pi over 2 is this point in the middle, where it comes to a pointy thing and hits the origin. Pi over 2 is an angle that makes the numerator, the numerator is long gone. I erased the derivative ages ago. But pi over 2 made the numerator 0, and it makes the denominator 0, which means it's kind of a special case here. The slope here isn't 0 and it's not undefined. If we zoom in on this, it looks like this. It's a point. It's a pointy, sharp thing. It doesn't have a slope. There's no vertical line, there's no horizontal line. It's just like it's called a cusp. We've talked a little bit before, especially during the section on L'Hopital's rule, about the difference between undefined, which gives you a slope, a vertical slope, and indeterminate, which is a 0 over 0 thing, and gives you weird nonsense. This is what an indeterminate slope looks like. It's different from the undefined slope. Undefined slope is vertical. Indeterminate slope, there is no tangent line at all. I think this video is about to cut off on me, so I'm going to be done talking about this. It's been a pleasure. Hope you enjoyed. This is Dave signing out.